right?
Homeomorphism is just a name, but essentially speaking, it is still it is also an isomorphism. So, isomorphism, the word isomorphism is used. So, we are always, whenever we are using this notion of a morphism, it means that we are inside some kind of objects, right? We don't speak about a morphism between a topological space and a group, right? So,
Okay.
so yeah, so they are of the same kind. So there is a hidden notion of this kind which we will later see is being reflected in the notion of a category. So isomorphism. So it's a morphism F from X to Y. So F is an isomorphism.
Uh,
I
I'm not seeing you.
I'm
Are you
sorry.
sharing your screen?
Sorry. Can you see my screen now?
Yes, now I can see your screen.
F is an isomorphism if there exists a G like this, such that F composed G is identity of Y and G composed F is identity of X. So both of them hold. Okay? So when you speak about sets, so when X, Y are sets, what we get is a bijection. When X, Y is a group or ring or such algebraic structures, we call them isomorphism, as you said.
Yes.
When it is a topological space, we call it a homeomorphism.
But with the homeomorphism, we require something more, right? That
No.
as
Remember, when we have topological space, our morphisms are automatically continuous. In books, they write, well, it's a continuous, and then and so many things. But the moment we take a categorical point of view, we see it is nothing else but an isomorphism. So saying that it is continuous and open and a bijection is nothing else but saying that F is continuous and G is continuous, and both of them, and it satisfies these two equations. So that is an isomorphism. Okay? Now, since you brought this one up, let me just put a ramification. So suppose if one of them holds, so F is a say suppose F has a left inverse. We often say F is left invertible or the more technical or better name is, we call it a split monomorphism. I'll say Y. Split monomorphism. If there exists a G such that G composed F is 1 upon X. Okay? And similarly, it is said to be right invertible or a split epimorphism such that, so you can see it's an isomorphism if and only if it is both a split epi and a split mono. Okay?
Okay, for the last one, the identity should be the Y.
Yes, correct. Thanks. Now, there is a, F is a monomorphism if it is left cancelable. What does it mean? So it means that you have this F and you have two further morphisms, say to some Z. Sorry. You have two further some Z. So such that F composed U is equal to, whenever you have this, it implies that U is equal to V. And F is said to be an epimorphism if it is right cancelable. See, the name is very, very natural. In this equation, it is cancelable from the left in equations like this. So, yeah. So over here, it looks like this. The picture is like this. So U composed F is equal to V composed F implies U is equal to V. Now, it can be readily shown that obviously every isomorphism is a split epi as well as a split mono. And every split epi is an epi. And every split mono is a mono. And that is very simple. Suppose F is a split epi. So what does it mean? There exists a right inverse. So there exists a G such that Fg is 1y. So F is something like this. Right? So now suppose, assume that UF is equal to VF. Well, then I'll write compose with G. That's pretty simple. So this implies UFG is equal to VFG, but then this is associative. So this is UFG, this is VFG, but this is 1. This is V1Y, but composition with identity gives me that same thing. So this is equal to V. Okay? So it's simple. But there is something more. If it is split epi and mono, then also it is iso. So iso is also split epi plus mono, or the other way round, even the split mono plus AP. Let me show this one. So suppose F is split AP, as I said. So F is split AP plus mono. So the situation is like this. Okay, and Fg is equal to 1y. So I have a right inverse. I want to produce a left inverse. So I want to produce a left inverse. So left inverse again. So let me look into this map GF. Now GF, okay, so let's try F G, and let me try something like this. So this is equal to G1Y, which is G. Okay, now that doesn't work. I want some so I want an H such that HF is 1x. So that's the problem. So this doesn't work. So I'll have to try and figure out. So 1x, let me try. So if I go by something, so let me see FG. FG, let me try it. FG is obviously a map from FG is a map from Y to Y. F is a map from X to Y. So this is a map from, this doesn't work, right? FGF is a map from, F goes from X to Y, G comes back. So this is a map from X to Y. Okay, that's fine. But let's see. This is FGF, which is FGF, yes, and then what did I say? It is a split AP. So split AP is FGF
Okay, but then when you say it's a mono, you mean that it's a 1-to-1. F is 1-to-1.
Yes, something like that, but it's better that we do not bring in that intuition. We just rely on this algebraic manipulation. Okay, and that the reason for this is, then it becomes, if we rely only on algebraic manipulation, we are sure of raising the proof in an element-free way. Because you see, the moment you say it's 1-to-1, you will go in for that explicit description that we don't want. Okay, so let's see.
Okay.
Yeah, in fact, it will be GF. It will be GF, but I'm just trying to find out way. So give a prop. So it will in fact be GF. So let's try. So G, FG is G1Y, that we did. That doesn't help. G is it has a right inverse, and it is also a mono. I have to use the fact that it is a mono. So
Okay. What do you say exactly when you say something is a mono? Because from what I've like what
I am
what
saying mono is just this. Whenever you have an equation like this, you should be able to cancel f from left hand side. Okay, so that's
Then F is a okay.
mono.
F is right. Okay.
Okay, so the only process is this. Okay, let's look into this FGF. Yeah, FGF. Let's look into this. So this is same as FGF, but FG is 1y. So this is F, but I can again write this as F1x. So the situation is FGF is equal to F1x, but F is a mono. F is mono. So it tells me I can cancel F from the left hand side. So GF is 1x. So you see, from the definition of split AP we got this. From the fact that F is a mono we got this. Okay? So that tells us that F is an iso. Okay? So the picture is this. Now we will in fact see, once we do a little more, we will see somewhat that in this top line there's a strange line of symmetry, as if here, and things almost are kind of mirror reflections. Okay, whatever happens, so we often will use this mirror reflection. It's usually called dual. So whatever holds on one side, its dual, its mirror reflection will hold on the other side. So we will see this later on. But the thing is, we will further see something more, and that is the real part of the story, that there will be several further sub classes over here, and similarly over here. Therefore, so they may not, firstly, these APs and split APs may not be same. So I'll speak on, so since using this duality, therefore I'll not always speak about both. If this is not the same, then in the mirror reflection this is also not the same. So okay, now I'll say, but once we have understood this duality, we will see that speaking about one is enough. Okay, so in general they may not be same. In general there can be several layers in between, none of them several distinct layers. But for instance, in sets, when we are considering sets and functions only, the situation is very, very simple. The situation is just this. And so similarly this. So what do I mean by saying, and what is this? This is precisely the surjections. And this is precisely the injections. And therefore this become the bijections. And the actual statement is, therefore, F is a surjection. If and only if. So, usually I give this as an exercise in Inset Theory.
Oh, okay.
F is a surjection. Show that these three are equivalent. So now in our language, it is a split epi, and C, F is an epi. You have already seen this part, and the other parts, and the other way round is F is injection. F is split mono, and F is mono. So they are all same. In case of sets. And this one is one of the most contentious ones. This is in fact equivalent to something called the axiom of choice. So in our sets and functions, the situation is much simpler. But there are places where the situation can be much more intensely different. So yeah, since you brought up this notion of an isomorphism, I had to bring in this. But we will see all of this slowly.
All right. Just for interest's sake, before you carry on, you said that that F is surjective, is equivalent to AP and also a split AP.
Yes.
But then, and you said that it's equivalent to axiom of choice. What about the right hand side? Is that equivalent to some other?
No. The right hand side strangely is much more simpler. The left hand side. Now, what is this axiom of choice? Let me try to explain this. Firstly, let me say it is something which is very much wanted, and it is something which is very much contested, to the extent that these are stories, but these actually reflect the real situation. So my first exit outside, I'm from India, so exit away from India was in Portugal, where I came for a conference. And I was a young boy, and quite an elderly person knocks at my room door the previous night of my lecture and says he will be interested in my talk. I know now, no one, I find someone interested. I was elated. Now I start giving my talk. After the first half an hour, I make a statement, and he says, "Are you going to use axiom of choice?" I said, this one can be done with something weaker, but later on I will be doing A, B, C, D, which is equivalent to axiom of choice. And he said immediately, "I am no more interested in your talk," and he leaves the room immediately. I had never seen this kind of this kind of a fact that if I don't like this, I am not going to listen. And so this was completely new. But then there was another person, you can search his name, he gave a big laughter and said, "You have antagonized the protagonist, but we are still here to listen to you." Now, this is the scenario. There are people who don't like it to that extent that the moment you use it, they are going just to stop listening to you. They are going to say it's just nonsense. And what is the reason for this? What is the reason for this? Before even saying what is this action of choice, let me say a word. What is the reason for this? Well, if you assume action of choice, you can get many nice things, But, for instance, you also get, well, I'm saying it in a very loose, simple way, because the actual technical thing is a little bit involved. It is known as the Banach-Tarski paradox.
Yes, I've read through it. I've tried to read through some of, I have an idea of what it is.
Yes, so roughly it means that using action of choice, if you give me one single cricket ball, I will give you 2 cricket balls, identical in volume, shape and everything to you. Will you believe this? Obviously not.
Yes.
So what's the problem? So now, coming back to Bernard, when I asked him, and later on we met a lot. Well, obviously, I'm like a student to him. So we met a lot, we interacted a lot, and what I learned from Bernard is the following. Mathematics is a game. So you have to have to make it very impersonal. If you use this, then you get this. It is all about if then. So if you assume this, then you get this. There is nothing known to be absolutely true. Nothing is absolutely false. So now, what is this big action of choice? To make this clear, let's make a thought experiment. So suppose I ask you, there are say 20 pairs of shoes in your room, and each one of them have black socks, pairs of black socks. I ask you, well, give me an algorithm by which a robot, will pick exactly one sock from each pair of socks for each of those 20 pairs. Can you give me that algorithm?
Okay, we can use the fact that the socks are
They are kept inside the shoes, yes.
Okay, so then we can choose one simple one whereby I say choose a sock that is in, say, the right shoe.
Good.
Something like that.
Good, yes. You can give several other rules, but you have given one. Yes, that's fine. Now suppose your robot cannot feel the shoes, cannot distinguish the shoes, cannot also understand that they are inside the shoes. So it just sees the socks. Can you make this robot pick one sock from each pair?
Okay. No, because there's infinitely many ways to choose. So, but then,
how do you say that it is being? Because you cannot make any reference to the shoe, to the left, to the right.
Mm-hmm.
Okay? So how do you make
Yes.
the robot understand now that I have to choose one sock from each pair without making any reference to boots, left boot, right boot, so on? Because the robot cannot understand the shoes.
I cannot think of a word at the moment.
Yeah, you cannot. The simple answer is you cannot. Yes, you cannot. And this is exactly axiom of choice. So what is it? So essentially what it does is, suppose you have one single set X. I say it is non-empty. Since it is non-empty, you can pick one element from there. That's fine. But now suppose there are several sets, say even sets, so several sets to make it clear. So suppose there are several sets. In fact, I don't know. There are several sets. How do you tell me that you would be able to choose exactly one element from each different each different set? That is exactly the problem that you said just now, that if you don't have a way to distinguish between these sets, to know that I am taking from this first set or the second set or blah blah blah, whatever. If you don't have a way to distinguish between sets from which you are taking, even if you tell me they are non-empty, I cannot guarantee you an algorithm to say that here is an algorithm which takes one from each. The fact that you would be able to distinguish between these sets is exactly the axiom of choice. So it says, given any, so that's why, so given any such thing, there exists a function. There exists a function which is from the union. So there exists a function which such that for each x in this collection, in whatever you may give, Cx is there.
Sure.
Yeah?
Okay.
Cx is there. So this is often called a choice function. In other words, let's give some. So suppose if I have a family of sets indexed by this, so it says that the product, what is this product? This product is precisely consisting of these choice functions. This is non-empty, and this is exactly the set of these choice functions. And each xi is non-empty. So the whole idea that, so if you don't assume axiom of choice, then okay, if I is finite, having 1, 2, 3, 4, or even countable, we know that since I is countable, so therefore we have a way to distinguish between x1, x2, x3 and so on. See, we can label these sets x1, x2, x3. x1 is not same as x2. We can make this label, so we can make this distinction, and therefore we will pick an element from x1, and I am sure it will not be from x2. Okay, so because I can distinguish. But the moment you cannot distinguish, see, from an arbitrary set, picking two distinct elements is a notion which is not algorithmically satisfiable. You cannot immediately. So at one go. Okay, so that is exactly the point. So you cannot distinguish, right? So the moment you say that it is countable, well, you have taken care of distinguishing. so goes. So, but the moment the set I of indexing set is uncountable, the choice part creeps in. You cannot anymore say that it is free of choice. So that's so essentially what you are telling me is, you take a product of 2 sets, 3 sets, 4 sets, countably many sets, it's non-empty. But without axiom of choice, you suddenly cannot take the product of more than countably many sets and say or prove that it is non-empty. So to do that, you need axiom of choice. And where does this come in? Well, the reason is that you have told me that F is an epi, and you want to say that it is a so epi implies a surjection is not a problem, but the problem is surjection implies a split epi. This is the part which involves choice. Why? What is the picture of a surjection? Well, the picture of a surjection is like this. Here is your x and y. The moment you give me a function, you have actually given me a partition of the set X. All of this have been taken to this. All of this have been taken to this. There could be something with single partition and so on. So it is something like this, and nothing is left over here because it is a surjection. So now if you have to give me this function, so that means if you have to give me a right inverse, so f g of y must be y. So there is only one way for where you have to do. That means you have to take g y to something here. So that means if you look into these sets f inverse y, this is a family of non-empty sets. And the exact problem is to choose one element from each one of these non-empty sets. That is exactly the case for axiom of choice. If you don't have axiom of choice, if you don't know, so if this y was finite or if this was countable, you could have done away with axiom of choice. But with a general y, you cannot. So therefore, you need axiom of choice to get hold of this g. And that's where axiom of choice surreptitiously creeps in.
Okay.
So that's where this is. So summarizing what I said over here, whenever I speak about sets and functions, to me axiom of choice is natural, normal. I don't question it. But I will be careful of things like Banach-Tarski. In fact, it's not only axiom of choice which is responsible for that. There is something called inadmissible transformations. What you are doing to that ball is actually you are actually taking an inadmissible transformation, and therefore you can do that. So I'll be careful there. I'll not allow those transformations. But why will I? So that happens on a much more closer analysis of that. So that's Bernard's. That's the take from Bernard. You take it bit by bit. You see that if this part of it is acceptable, I accept it. This part is not, I don't, and this part is not because of this, so I don't accept this. So it is, nothing is completely, what do you say, beautiful, faultless, and nothing is completely bad and nonsense. So each one has its own perspective. That's the first story that is coming up over here. And we have to keep that in mind, and this is a very, very categorical way of looking into things, because category theory teaches each thing of, there are several types of things in this world. Each type transforms in its own way. Each type behaves in its own way. You cannot impose the behavior and nature and intuition from one type into another. You shouldn't do that. So,
Okay.
you should consider these types in segregation separately, one, and in communion means, well, this happens in this type, but this doesn't happen in this type. Okay, so look at it from both of these perspectives. Look at their similarities, look at their dissimilarities, and and keeping in mind that they are different types. So that is the more important part of the story.
Okay. Just to ask, because I've also realized, for instance, there's a sort of layering, if I were to call it that, in mathematics. Like when you consider formal set theory, and then you look at the axioms, and then you consider, say, like the axiom of foundation, and then you sort of see this layering of, first you have like the empty, and then the one that contains the empty, and it's sort of like there's this sort of hierarchy of like these sets that layer on top of each other. But then you also get to see those sort of structures, or that sort of layering as well. Is that sort of the case in what you had shown me, that you will have a split epimorphism, and then there would exist certain other structures in between, and then maybe you would have like an epimorphism at the very end?
Yes,
On
yes.
a purely theoretical sense.
Yes. This layering that you say, okay, this one and this one, I would not say, although it is. There are layers. I would still like to. Okay, yes, you can still call them layers. Now, coming back to sets and that one which you said, obviously, this is often called the, in set theory, this is known as the von Neumann universe.
Yes.
So how does it start? It starts with this. And then it takes the power set. Then it takes the power set of this. Well, this is a bold 2, this is. And then it takes It goes on like this. It takes the so power set means set of all subsets. So then it takes the this is 4 and so on. So for each n, so the idea is like this. So the whole idea is there is this huge so you have these numbers. Previously, before we say about this, we must start by saying there are these numbers which we call natural numbers. So it starts from this, and then 1, you can look upon it as this, or you can look upon it as a successor of this also. Now what is successor? If you give me a set X, a successor of X is nothing else but X union X. So for instance, if you have the set of reals, now the successor of reals is a set which has all the real numbers and then another strange point which is that set itself, right? So yeah, so here it carries on in this way, and there is an axiom called the axiom of infinity.
Yes.
Which says there exists a small set say X such that empty set belongs to X, and if X belongs to X, it implies that the successor of X belongs to X. Now something about this small and big. Now the problem with why we had to bring in this axiomatic form of set theory is obviously the one unique paradox which comes to our mind is Russell's paradox. And that essentially says that essentially tells us that if you look into this sentence, there are two sides of this. So this is a relationship kind of a thing. Now the left hand side you are saying elements, the right hand side you are saying sets and so on. In a set only point of view, both of these are sets. Okay. So then you cannot give equal rights to both the left and the right. That means you have to restrict. If you don't, you'll end up with problems like Russell's paradox. Why? Because you will take this set T such that it by extension this is a well-formed formula. So now when if T belongs to T, then it means T doesn't belong to T. And if T doesn't belong to T, by this formula again it means this. So you have this paradox. And what's the problem? The problem is exactly this. You have put no restrictions. Now if you restrict the left hand side, That means everything cannot be elements. Okay? So that's when you say, so this is essentially the Neumann-Bernes-Gödel model. What does this say? This says it defines a set to be small. What is a small set? That exists, and so X is small. If there exists a set X such that X belongs to X. So if a set is small, if it is capable of being an element of some set, if it is capable of being an element, that is the meaning of it being small. So large, it means not small. That means it is never possible to make it an element. So this is an example of a set which is not small. It is a large set. Okay?
Yes.
So now the
What other term do they use besides small again? I mean large. There's another term that they
yes,
use.
yes, large, or people also call it a proper class.
Oh yes, classes.
Sets are also called classes. So what they call set or a class, set or class is class or set.
Okay.
I use the word small set and a large set.
Okay. No.
Yeah, so this is the Neumann. But if you restrict the right, what we get is a ZF, Zermelo-Fraenkel.
Okay.
So what is happening over here? You suddenly have entities. So you have sets, you have on the right you have sets, but suddenly you have a ghost. You don't have anything on the right. Why? Because say for instance, what we call large, they are not eligible as being elements of something, so you cannot have anything which contain them. So that itself cannot be seen. You cannot hold it. It becomes a formula. So often people say that what is ZF is they are ghosts of entities. Formulas are entities, and then you could catch them, hold them, work with them, and suddenly when it becomes big, it vanishes. It becomes a ghost. So that's a.
Oh, okay.
So that's ZF, and that is precisely the reason why I don't like ZF, because I will need to place my hand. I need a handle to crank and to manipulate with things which are also large. So I cannot suddenly communicate with ghosts. So I need someone whose ear I can catch. So I need this X, even if it is large. So I need to hold it. So that's why I often use, and mostly I like this NVG form of set theory, where you can hold it. And most people who work in category theory or topology, they do it because in topology it is quite normal that you have very large sets coming up in practice. So they need to hold them, they need to manipulate with them, they need to take operations on them, and so they need to hold them, and they cannot do it with a ghost. So therefore they need NBG. So that's why they take this form. There are obviously several other forms of set theory. There are several other forms of set theory. Well known, there is another one which is the Klein-Moore set theory and so on. There is one which is also becoming a little more contentious and competitor possibly because of this big data and such things coming in. In computer science they use it. It's this Klein-Moore form of set theory which is also coming up, and they need that formulation in their studies with data structures and so on and so forth, but I don't know much of it. So that's also another form of set theory. So this is not the only two. There are several other forms. With each form, for instance, you have, so the actual kind of set theory that we will be using is this, because axiom of choice is known now to be something which do not follow, which is called, it is independent of the usual axioms of set theory. So it is an extra axiom. So the actual system that we will be working is NBG plus axiom of choice. Okay? So, so that's the place where, so now saying that, so it says axiom of infinity. So obviously the notion of strict large and small comes at the beginning, and then the axiom of infinity says that there exists a small set which contains all this, so which contains for each n the successor of n. So n plus 1 is the successor of n for each such. And then that becomes the model of the smallest such set which satisfies this. A set which satisfies this is often called an inductive set. And the smallest inductive set becomes the natural numbers. And that has its piano arithmetic and so on. It can be proved. It has a piano arithmetic, so it makes a ordered semi-ring and so on and so forth. And everything else then fine follows. But then what then starts the next phase, which says that, well, even if you take natural numbers for as far as the sets are concerned, so every set, there cannot exist, so this is another important thing, there cannot exist a bijection, a surjective function from x to 2 to the power x. So in particular it is saying that the set of all subsets of x is huge, it is much more than x. There cannot exist a surjection. So that means far from, and the proof is very, very simple. Suppose if it was a surjection, if this is a surjection, so then let me take this. So it's almost same as the Russell's paradox kind of a thing. Okay? But since you have told me that this is a surjection, this is ft, for some t, then t belongs to t if and only if t doesn't belong to t. So that's the same. That's a simple way. So it's the same story. It is usually called the Cantor's diagonalization principle, because it's the same. It's essentially the same. Okay, let me speak on this idea. These ideas are very very deep, entrenching ideas. You know how Cantor came up with the proof that rational numbers are not countable?
Yes.
What does he do? Well, he says he first assumes that every real number has a unique, infinite decimal representation. Right? So this is the first thing that he needs. Has a unique, infinite decimal representation. So then he takes Bn. He takes any set, any count, any sequence of real numbers. So suppose I write down its decimal because so I am so suppose, in fact, to be specific, let me take this. Okay. So then what do I do? This looks like this. Okay, and it goes on. Now he makes a beautiful choice. He says, let's look into these numbers. Let's look into these numbers. So this, what I meant is this one. These things. Because each one of these are either they are 0, 1, 2 up to n. Okay. So now I take this number. So I define this number, say Bn. Let me take another one. Say Cn. This is 1 if Bnn is even, and 0 if Bnn is odd. And I look into this number. Now this C cannot be B1, it cannot be B2, it cannot be B3, and so on. So this is neither, it's not any one of these Bn for all. So what did he prove? If you give me any countable set of numbers, real numbers, there is always a real number which is is not in that countable set. So in particular, rationals is not countable. If you said it was, I'm sorry, the reals is not countable. Why? If you said it was countable, there is a each one of these real numbers can be written as a sequence. So as a countable sequence like this, in Bn's, but I can produce what will be this C then. So that was his argument. So now there is nothing special about being decimal. Today's world, you can replace this by binary. Why? What is the hell in a decimal representation? How are you getting it? You first take a unit interval, divide it up into 10 parts. Okay? And then what is this? You take the first thing first interval where it falls. Then you expand this. You multiply this 10 times. Again do the same procedure. And see the interval where it falls. That is your second one. And so on. Right? So that's how you're going.
Yes.
That's how you're exactly getting these numbers. And why do the which points have 2? The ones which fall on these endpoints. So precisely this, if you have something like this, precisely the case, the numbers which are of the form k by 10 to the power n, where k is some number, right? These are the numbers. So all the numbers which are of the 1/10, 2/10, 3/10, they are going to have 2 representations, right? Then again, if you go on this level, so 1 by 100, 0, 0, 1 by so this is where k are the numbers 0, 1 to up to 10 to the power n, right? So these are precisely the numbers as you vary your n and k, which have exactly 2 decimal representations, nothing else. Okay?
Okay.
So there is nothing special about decimal. You do it, replace 10 by 2. These numbers will be 0 or 1. Again, you can come up with a similar kind of right? Now, why did I do this? Well, this 2 business now helps us in understanding what he did over here. Because what is 2 to the power x? You can, as if you know that, 2 to the power x is the set of all functions from 2 to the power x, means it's the set of all functions from x to 2. Right? Okay. So giving me what is this? Because you just tell me which function, which elements go to. So as if you have written down x like this. So you can think of it like this. If it is so, some of the points where you have made it, highlighted it, or if this is much more, so where these are highlighted, these are the places where it takes 1. Those where it is dark, those places it takes the value 0. Right?
Yes.
In other words, choosing a subset, so when you are choosing this subset, you are only telling me that this is the place where the color is bright. Right? These are the places where it is 1. The rest is 0. Right?
Yes.
So that's how you're choosing your subset. So now try to see, is the picture like this. For each point x, as if this is the xth point, right? So as if you're writing like this, don't think of a decimal representation, but think for as if you could write down like this list of natural numbers, you could write down all the elements of the positions for all these elements of x, and precisely at those positions where you have 1, you have that x coming up. Something like this. So this is this function f. Another function g is possibly something like this. Okay?
Okay.
All right. Now the question is, so this corresponds, so remember, this place corresponds to a point in x, right? So what you are taking those points x such that x doesn't belong to fx. So it's essentially something, so it's you're actually kind of doing this. Why? Here your points were this first place, second place, third place, and so on. So here what you're doing, you're taking all those integers and so all those places, C is this function, such that n is not in Cn. So exactly this is the same. You're using this even and odd to make this distinction, right? So you're actually using this same story over here. So what are you doing? If this place for a function x, you're taking for this corresponding xth place, if this is dark. So you are taking all those places which are dark for those x's, those places which are not in your fx for each f, right?
Just go over that again.
So what are you doing over here? You are using a dichotomy, right? Even or odd. Over here, right? Now as you said over here, what's the corresponding parallel picture? These are what I have written over here. This means there is a place which we might write like this, say the place for x, this is the place for x prime, and so on, right? Because in this place what you are going to observe is this is bright, means this value is 1, right? So here this is the place for y, this is the place for y prime, and so on. So let me write it in this way. This is the place where it is 1. Right? So this is how G looks like. Now, giving a subset means just giving a sequence, some ones, right?
Yes.
Okay. Giving a subset, so giving some ones just mean giving a function like this. Okay. Now you have told me that this, let me give this function another name, say phi. Okay? Now phi x, for each x in x, phi x is a subset of x. Right? So for each x, phi x is one of these lines, one of these rows.
Yes. Yes.
So now how are you choosing your subset now? Look, phi x is a suitable row. For each x. So this is your phi x. Phi x prime could be somewhere else. Right?
Yes.
Okay. Now what do? Look into this row for phi x. If there is a 1 here, don't take it. But if this is the row for phi x prime, and this place is dark, so in other words this is a 0 over here, take that. So you take all those x's where in the row for phi x and the column, so you look into x phi x position. If there is 1, you don't take it. If there is 0, you take it. Right?
Okay.
That's what you do. Okay? Till this point there was no, and therefore this t that you have made in this way will make its place somewhere here, because you have already taken a subset. Okay? Will make its place somewhere here in this. It will be some one of the rows, because it is a subset. Okay. So now the next question, the real problem starts the next place. You have told me that this is a surjection. So this t is actually equal to some phi t.
Yes.
So actually this t is some phi of it. But then, so this is some phi of some t. But then, by the choice that you said, this place is 0. T phi t position is 0. That's how you chose your phi t.
Yes.
But then, since this is this place must have the value 1. Because this t, so t is a member of t. Right? It means that there must be a 1 over here. But since it is the member of phi t, this place must have the value 0. So it says t must not belong to t. And the reverse also happens. If t doesn't belong to t, that means this is going to have, if t doesn't belong to t, this place is going to have the value 1. If this value have the 1, then it is a member of phi t.
Yeah.
So you cannot determine what value will be here. If you say that this is some phi t, the problem started here. Okay? So you see, this is exactly, if you write it out in this way, you're using, it is exactly some kind of diagonal argument. Right? T phi t. That's what you're looking at. N, the value of b at 1, 2, so you're looking into that, right?
Okay.
So it's the same idea, same idea. The idea wise it's the same thing. Why I spent this time, you can think now how to go from tables to this alternative form and so on and so forth. This manipulation, yeah.
Okay.
So I don't know whether you thought this was trivial or, but I think this should be understood that this is nothing else but this plain tabular form as we see this proof and this proof are exactly the same. Now, what's the upshot of this? So it says that you started off like this and you said that you gave me natural numbers, okay, the smallest inductive set. So then you have the power set of this, the set of all subsets of this. That is definitely not countable because this says there is no bijection. Then you have this. And it carries on. And Cantor goes on and on and on to give a whole series of infinite such things, which he calls them cardinal numbers, and invents a whole lot of arithmetic for it, which is essentially the arithmetic of bijection, nothing else. He didn't do anything more. It's the arithmetic of isomorphisms and bijections and so on and so forth, nothing more. Obviously applied to sets and their specific things. So that's what he did. And then he comes up with this whole set of cardinals, and there's a beautiful book, if you can download it. It's called Sierpinski, Cardinal and Ordinal Numbers. It is an old-fashioned book. It tells you a story. I don't remember having seen an exercise in that book. But it is going to present you a story. And that story, it's like a story in Alice in Wonderland. It will keep you engaged. I remember to have read this book while I was traveling in a train. Well, quite a long distance. Around, say, from here to Cape Town. Yeah, 2 days journey. I read it in that. And it's a fantastic book. You will not, the way it is written, the way, unless you read it, you will not be able to, it is not describable. But the imagery that it gives, how to create these things. So, the whole point then comes up is, how do we proceed after? He finds that there are two, so there is a little better kind of cardinals, which are in between two cardinal numbers, and they are called ordinal numbers. And so there is again this ordinal numbers, he writes like this. These are in the finite stage they are still the same, but in the infinite stage there are many in between. So then there is something called 2 omega naught, then there is something called 3 omega naught, and so on. It goes on to omega naught square plus 1, and then it goes on to omega naught square plus omega naught. So polynomials, all polynomials in omega naught. And it carries on and on. Finally, it comes to omega 1, which is nothing else but corresponds to this cardinal. 2 to the power. Well, this is again another. So then I shouldn't say this because this itself is another hypothesis. And it carries on and on
Yes.
and on. So all these ordinals. Alright? So it carries on like this until, so what the von Neumann universe looks like is this. So it's based on these ordinals. So alpha is an ordinal. So this is empty set if alpha is 0. This is 2 to the power v beta if alpha is beta plus 1. So that's exactly omega plus 2 means this plus 1, okay, and so on. So it means that if it is, so such things are often called non-limit ordinals. So if alpha is a non-limit ordinal, these are precisely the ones which look like this. And then if it is so, it has a predecessor which is beta, for beta. For beta we have already constructed, and then you take its power set. And else what is it? Otherwise, it is the join. If alpha, if otherwise, we just say otherwise. Or in other words, at limit stage we collect. We say it in this way: at limit stage we collect, at non-limit stage we construct by taking the power set. And that's how we carry on. And I'm sorry. Yeah, this is, so this is the von Neumann set theoretic universe. Sorry, this is my description of V alpha. Yes, I'm right. And then V, which is the set von Neumann universe, it is this join. So every set comes up in one of these classes. So that's what, as you said, it's a kind of a hierarchical structure, right? Starting from the empty set. And if you see, well, this was the original starting point of the notion of a structure, but it was abandoned for obvious reasons, but still it is. So what is a group structure, for instance? So it's a X is a set. First, let's take so then you have a binary operation.
Okay, Doctor, just before we carry, just before you say, the book that you suggested, I was actually using a book by Kenneth Kuhnen called The Foundations of Mathematics. Now, he also paints the picture, but then the way he presents it is that basically you have the ordinals, and as you said, when the ordinals are finite, then you have that the ordinals are exactly the cardinals. But then when you get the infinite ordinals, they sort of start to clump together. So after the natural numbers, you'll get a clumping of them together, in the sense that you're not increasing the size, the cardinality is not increasing up until a certain point, or up until, like you said, when we start to collect.
Correct.
So
correct.
You get this, like I said, how do I say, clumping together. So
Yes.
the ordinals would increase, or let me say that the order would increase, but then the cardinality remains the same up
Correct.
until we collect. Then
Correct. Exactly so.
it carries on like that.
Yes. Exactly so. Exactly so.
Mm.
So that's the whole idea. So omega naught plus 1 is just you take a copy of omega naught and place another element. So these ordered sets are often called well ordered sets, in which well ordered means every subset has a smallest element. Okay?
Yes.
Yeah. So every subset has a
Okay.
smallest element. So, and your increasing over here is by making the smallest well ordered set larger than that. Yeah?
Yes.
So that's how you're increasing. So the best way is to just put one single point which is larger than every one of them, and that makes it a well ordered set again, but it is bigger than the one with which you started. So that's the whole idea.
Oh,
So, and you carry on and on and on in this way, and that's how you get the idea of these finite sums and so on. So, yes, what you're saying is right. Yes, Kunen's book is also good. It's not bad. Yeah, why? It's a very good book. But the difference between Kunen and the Sierpinski's Cardinal and Ordinals is this one is a storybook.
oh, right. Yes, because now with Kunin, like the it's more of
It's a textbook.
graduate. Yes, it's a graduate thing, but
Yeah.
it doesn't hold your hands too much. It doesn't hold
Yeah, it's a textbook. So it is a very good book. It's a textbook, but the problem, but I'm not saying the problem, but Sierpinski is not a textbook. It is definitely not a textbook. It is a very old style writing, and it's a fantastic book in the sense it's like a storybook. It tells a story, it narrates a story. Obviously, this was the way of writing almost 100 years back, which I also like, but unfortunately, you cannot maintain it these days.
But then, is it the same Sapinski who wrote what's this differential geometry textbooks?
Yes,
Or is
exactly the same. Vaclav Sierpinski.
okay.
Or I have W. Sierpinski. I have forgotten the full name. The same one. He worked in differential geometry. He worked in set theory. He worked in topology. Well, he is a very established mathematician. So, but the style of writing is different. He kind of tells you how to play around with these sets. Well, I don't know. You should make
No,
your
definitely
decision
look
for
up.
yourself. For instance, there are very nice textbooks like Apostol and others, but I loved this book by Konrad Knopp on infinite series. Let me tell you why. Well, he says, I want to make a sum, and then he comes up and says, he comes up with the idea of a sum and prove something, but then he shows that this series doesn't have a sum. So then he says, but how do I ensure this nonsense? Because things are going smaller and smaller and smaller, but in my definition, I cannot make it having a sum. Where is the problem? Suppose I increase each one of the terms a little bit. Does it also become? Yes, it will obviously then become also. But if I decrease each one of the terms a little bit, then it comes to show that if you decrease quite a bit, you can make it summable. If you increase a little bit from that quite a bit, you can make it not summable. So as if there is a boundary between this summability and insummability. So he's trying to reach this, and how to reach this, and this is how he explains the comparison lemma, the comparison, comparison test and the root test and so on. And the story that he brings up like this, let's decrease a little bit, let's increase a little, it adds infinite amount of intuition into the picture. The technical details are there, everything in apostole, but this intuition only comes up when you discuss, when you put this down in a story. And this is what these old textbooks used to do. They used to build up this intuition, and it took pages and pages to write this. So I like them because of the simple fact that it brings out this intuition much better. So same with Sierpinski. So it brings out this intuition about this infinite sets, this cardinals and ordinals. Yeah.
Okay. We can stop here today, and
yeah.
One with regard to the whole style of writing, to some extent, with me, like I said, reading Kunen's book and the others, it feels more like whenever now you start doing mathematics or axiomatics, some usually term it. It's as if though, at least with me and my experience, it's as if though they're saying that need your intuition there, like the formal, the precise definitions, and it's as if though it's a completely different way of looking at mathematics from the way you describe how Sierpinski and Knopp also wrote their text. I don't know if that makes sense.
Yeah. You see, there is a tension here. There is a tension here. But this tension is everywhere. When you go to a good hotel, you have a very nice plate food, and if you ask for the chef, he or she might even come and explain how is it done and so on. But the problem is, you will not be allowed to enter the kitchen. You will not be allowed to enter the kitchen, and the kitchen almost surely will be as dirty and messed up as anything else. Now, the dirt and the mess that the kitchen is doesn't say it is a bad place, because that's where the food is being made. And it's the same over here. So when you start thinking about things, the intuition is obviously needs to be very, very strong. You must develop a feeling about these objects. Now, when you present it, the presentation must be very, very formal. I think
Okay.
the kitchen business, the chef tells you this. The kitchen, how far dirty and a mess it might look, but the food, the plate that comes to you looks absolutely uh, not only delicious, but it looks also good, right?
Yes.
So that's the so over here it means that it must be written formally, and it must be presented very neatly, coherently, formally in this theoretic language. But understanding about it and trying to think about it, we cannot do it that formally.
Mm.
That is where the intuition comes and creeps into the picture. That is where choice creeps into the picture. There are stages, obviously, where we have to see which one is a better candidate and so on and so forth. And there are several arguments for a choice, and one might accept another argument and go for another choice than you have done. That's true. But arguments for and against are also there. So there is a lot of subjectivity in this in the preparation. So a lot of dirt over there, right? But when it is prepared and presented, it seems as if it is absolutely faultless, right? And
Yes.
yeah, but that is not the that is the final dish that is coming out to you. And the thing about these old and new textbooks is precisely here. I like those old textbooks because they were honest, and they didn't. I'm not saying people are dishonest now, but what I'm saying, they had the guts to put that dirt in front of you.
Okay.
They put down that dirt in front of you. But now we don't. Nobody will publish that dirt. It comes only in. It only comes when you when you are in discussions, when you are discussing, when you are speaking. People speak about that dirt, that intuition, that picture, but it doesn't quite come up in the textbook as it used to in previous days textbooks. So the writing style has changed, but not the creation style.
All right. And also, just to ask, was Banach's view, or can it be considered that of like a because of a constructivist point of view, or what?
No, a constructivist is someone who doesn't, for instance, believe in double negation, or in the fact that the world has only two truth values, or in axiom of choice kind of things, and so on. So avoiding these principles is one of the basic tenets of constructivism, although there is much more to it than just it. But these are obviously signs. What Bernard Banashevsky tells is that, and that is much more than this. He doesn't say that you have to be constructivist. He doesn't say you have to. It's not about being that, but rather thinking in this way. If you assume this, that means if you are in the shoes of a constructivist, then you see it in this way. If you are in the shoes of this person, of another person who has another kind of logic, you see it in this way. And if you ask him which one of it is true, well, he will possibly say none.
Okay.
Well, I don't know whether this story would. Well, this is a very, very old Indian as well as this story is also. It's difficult to say whether it is really Indian or not, because I have heard this variation of this story also in Czechoslovakia and other places in Middle East European countries. So it could be a common civilization which existed long back. The story is coming from there. So roughly it is like this. I heard it obviously in my Indian past mythology. So, but if I strip away those things, the main story is this. So the king finds a dream that he is in a war battlefield, completely exhausted, no one around him. He's trying to find a food and somehow gets hold of a fruit which had fallen in an abandoned tree. The moment he catches hold of that fruit, an eagle from nowhere comes in and grabs it and runs away. And he is too tired to grab it back or kill that eagle and get that food and so on. And with that anxiety and this, he wakes up half dread that he will die now. And he sees that he is in his cozy bedroom over this, in his palace. And he tells this story to everyone in the court next day and asks, which one is truth? Myself dying in that battlefield, or that I was on my bed and I came to you to tell this story? Everyone has different interpretations, and then asks a seer. The word seer is also strange. It is in Sanskrit as well as in past old Polish languages. So whatever, the seer means someone who can see through, who has seen a lot of things and who can see through things. So he asks a seer, and the seer says, neither one of it is true. You are the only truth, and everything rests within you. You are the only truth. So it's the same thing. Neither is this constructivist thing true, nor is this axiom of choice true. Everything sits in your damn head. If you cut it out, nothing will remain. Okay? So, you are the only truth. So there is no point in identifying yourself with some idea which comes out of your head, means your thinking process. There is no point in doing so. There is no point in doing so. So, well, it was the same question, and in fact, so this reconciles this attitude that, well, neither is constructivism true. There are several. There are constructivism, there is Platonism, there is finitism, there is many other versions which even work in mathematics. There are mathematicians with this strong philosophical beliefs, but none of them is true. So, and you would have deprived yourself the joys and merits of other systems if you completely subscribed yourself to one of them. So it's best to look at it in this way. If I take it, if I am in this foot, if I assume these, then I can get this. If I assume this, then I can get this. Okay, so it's much better to have a categorical point of view. It's much better to have a pragmatic point of view than subscribing to a single point of view. That's the take over here.
But then others would argue that if, for instance, the way it sounds, that view of if taking mathematics as a game or as a manipulation of just what you get if you assume this, and if you get what you get if you assume that, they'll just say that you are subscribing to the formalist point of view, whereby you don't necessarily say that maybe things exist outside ourselves or in ourselves. It's just we're playing a game with what's this, symbols. Then those symbols are on a piece of paper or in our heads, and we just deriving, or like we're just playing this game. So it's also considered a certain kind of point of view, or the formalist point of view.
Yes. This is a complete formalist point of view. But the formalist point of view doesn't subscribe to any particular subsystem of that formalism. And
Yes.
Yeah, it's a complete formalist point of view. Yes, you're right. And so what's the problem?
No, it's not a problem. The thing is, now, if you go into like the philosophical argument, is that they liken formalism or formalists to like
Agnostics.
How do I, agnostics? Yes. While say the Platonists are more likened to the what's this? The theists, and then the others maybe like the atheists. So they it's sort of like you said, there's finitism and the others, but then those ones are usually considered sub schools of constructivism.
Yeah.
While Platonism is more seen as a theist point of view, where you believe in this ideal world that exists in the ideal, outside ourselves, and so forth. So.
Yeah. The only point of difference is. Yeah. Please complete.
I'm not saying there's anything wrong with it, but I think a lot of modern mathematics, even though the actual mathematician might not necessarily subscribe to describing himself or herself as a pure formalist, but modern mathematics takes on that view in presentation, if I were to say it like that.
Yeah, obviously it takes that in presentation very much.
Yes.
But it is again a Platonism, but I would say a neo kind of a thing, because Platonism kind of says that there exists something and we are discovering it, and this something is beyond ourselves. What I am just saying, it is nothing is beyond ourselves. It is all within us. That's what I am saying. Yes, it is a world. It is another world. It's a world of formulas. And we are discovering them. Yes, it is true. But that is within ourselves. That's what I am saying. And
Okay.
if it is really beyond, it is within ourselves. That's what I'm saying.
Okay, but then which stance would you take if I were to ask you then that it's also a very deep philosophical question, mathematical philosophical question of whether mathematics is discovered or invented? Where would you stand?
Discovered.
Okay.
It is the moment you have crystallized a set of axioms. That means you have the moment, and you have decided upon the body of logic with which you are going to deduce. You have created the world. You have created the world of formulae that is going to be true, and you have created the world of formulas that is going to be provable. Now it is upon the mathematician to discover the ones and the proofs themselves. So the moment you did it, the world started to exist. It existed. Okay? If you take the usual classical Boolean logic kind of a system, you tell me that certain formulas alpha, beta, gamma are certain things are certain atomic formulas, and you know how to make your formulas in this theory. The moment you said this, you know what are all your well-formed formulae. From this set of well-formed formulae, you have chosen alpha, beta, gamma as your axioms. Okay? And then you are telling me that if alpha, beta, gamma are your axioms, from here you have a proof of tau. As how do you prove it? Alpha and alpha implies beta, and alpha implies psi gives you psi. Psi and psi implies gamma gives you tau. So that's your rule of deduction. So tau is a provable formula, and so you create these proofs. You discovered these proofs. Okay. All right. You will say that if this is it, then I can apply a machine. Yes, you can. You can apply a machine, but you must also remember the machine's strength is only up to a computable limit. It cannot go beyond computation. But you can somehow, this is the other side of the story, and it goes possibly much more deeper into things, into trying to understand things which are algebraic and which are geometric and blah blah blah. So it gets into very, very deep issues over here when I am saying that a machine can only do up to a computable limit. So, but you still can do. There are certain theorems which was proved, for instance, as examples I can give, which cannot be done by starting from the axioms. You cannot come to that theorem unless at certain point you need a non-computable step. But that step is still provable step, but it is a non-constructivist step. You don't have that proof. You don't have that theorem in constructivist framework. So you have to apply certain non-constructive principles, which you can do, but which the machine will not be able to find out. So this is where your choice and your uh, things creep in very strangely, and you get beautiful theorems. But uh, just using machines, you will get very intricate theorems, though very deep theorems also, but they will be within that computable limit. So, mm,
Okay, but if I were to say,
uh,
you if I were to say, because you are saying mathematics, for instance, is discovered, but then if I were to say or put it to you then that during the crystallize, or like you said, when you write down the axioms,
yes,
it there is the possibility of, say, the mathematician or the formalist inventing the axioms in which they would like to, say, uh, discover the proofs
no,
of like the
no,
logic
no, no, no,
system.
no. You start off with alpha, beta, gamma. I start off with alpha and tau, and somehow someone else later comes and says, well, alpha and tau, whatever you can do with it, you can do with it alpha, beta, gamma also. And then somebody else possibly started with beta and tau, and then he says that, well, if you do with beta and tau, you get a different system. So you can definitely take choices. Whatever you choose, you will get a world. That world may be a nonsensical world. For instance, if you take alpha and not alpha with a Boolean logic, you will get a nonsensical world. You will not get anything more than that. It's a nonsensical
Yes.
world. So, so the fact that today you have a theory A well established only says that that choice was good. Choice of the basic axioms for A was good. If you chose something else, you would have another theory A prime.
Mm.
Well, it is not yet discovered. So it doesn't mean that A is good and therefore A is the only theory possible.
Yes, and that's not what I'm saying. I'm just saying that I would take the stance that mathematics actually sits somewhere in between where it's both invented and discovered.
Okay. Okay, that is your stance. I accept it. But I will not.
Okay.
I will still say it is discovered because I don't have a way to say it is invented. Mm.
Oh, okay. Because my argument would or the crux of my argument would lie in the sense that the invention would lie or would be in the step where we write down our axioms.
Okay.
Be it that the axioms, maybe we guide it by our intuition when we try and write down the axioms, or we could, as you said, as the formalist might choose a nonsensical set of axioms to begin with, whereby they're not necessarily guided by intuition. So I think like I said, the invention will follow. Yes, we would agree as formalists on the framework, or like the logic that we use, and then the discoveries then would happen at that point where we provide the proofs and show how the proofs come about. That's what I think.
Okay. How one comes up, yes, obviously, guided by his or her intuition and his viewpoint, that he comes up with a choice. If you like to call this selection of the basic facts as an invention, well, I will think that it is a name given to this choice. He could have chosen something else, but it is his own system that made him make that choice. And since in a complete formalist view that I am taking, in which everything is a discovery and not an this is equally likely like any other choice, I cannot therefore give any credit to this choice or a successful theory or whatever as an invention. I would still give it the name of a discovery. He discovered this, and well, it became successful. It became, yeah. It went down the line. It passed the test of time, and that's why it is successful. So, yeah, but I would still call it, because a complete formalist would not have the within his dictionary this word invention. A complete formalist cannot have this word invention. It is only about discovery that he can think of. Invention means if you were to take it exactly as the English word says, that you created something new out of. But being a formalist, I cannot say it was new. It was there. Being a complete formalist, I know it was there. So, it is not new. The new part of it, or the little part of it where this goes, is this person's way of looking into the things and selecting these. So that's why I said, if you call this selection, procedure, invention, you have changed the meaning of the word invention as Webster defines, and well, okay, then I accept. But that's my view. That's my point of view as being a complete formalist. You see, Platonism is, for me, Platonism is there. Yes, obviously there, but it is inside me, not outside. So I cannot accept anything outside myself. Everything is inside me. It's only the fact that I recognize or I don't recognize, I distinguish or I don't distinguish, and so on. Yeah. So that's a philosophical issue. Yes, I agree. So my stance is very much formalist stance, and a very, very complete formalist stance, not a subset of it.
Okay.
Yeah. Okay.
So, Doctor, will you just send me the notes then, and just go through some of them? But I think what
I recorded today's session, so I'll send you both. Okay.
Okay. Yes,
All right.
I appreciate that.
Okay.
Okay then.